In this video, we're going to be taking a look at an introduction to probability theory. And all of the stuff that we'll be doing in the probability section is very much a brief introduction to probability theory, in the sense that probability theory itself is actually a rather large undertaking if you're going to take a look at all of probability theory. That can take up an entire course. And so all that we're going to be doing this quarter is getting enough probability theory to link together what we've been doing so far with the statistics with what's going to come next in statistics. There is a overlap between statistics and probability, but probability is actually a separate field of study, and we're getting just a little bit of an introduction to this. So when we talk about probability, what is it exactly that probability measures? Okay, probability is a measurement of how likely an event or series of events is to occur. Okay, when we measure a probability, what we're talking about is how likely is something to occur. All probabilities must be between 0, which would represent an event that is impossible, and 1, which would represent an event that is said to be certain to occur. Okay, so all probabilities are going to be somewhere between 0 and 1 inclusive, meaning they can be equal to 0 at the lowest, they can be equal to 1 at the highest, or somewhere in between. Now that's if you're going to represent them as decimals. If you're doing percentages, we would be looking at 0% to 100%. We can't have something that happens less than none of the time, and we can't have something that happens more than all of the time. In this section, we'll switch back and forth between decimal notation, percent notation, fraction notation. I have no personal preference which one you use, but if you are going to use fraction notation, it's important to make sure that all of your fractions get into lowest terms when you're computing probabilities. A couple of items about notation. So probability notation. Events are typically labeled with capital letters. A, B, C, and so forth. A lot of textbooks will just use A and B for almost everything, which is fine. But if I were calculating the probability that, I don't know, individuals in a group preferred donuts, for example, I might use the capital letter D to represent probability of donut. I think it's handy when you're computing probabilities if you can use a capital letter that represents the thing that it's standing for. That makes it easier to follow the written work. Now, if you see the capital letter P and then in parentheses some other capital letter, what that is read as, you would read this as P of A or probability of A. And so what that notation actually represents is the probability that event A occurs. And similarly, if you wanted to find the probability of event B, there would be a B in here. If you wanted to find the probability of event R, there would be an R in here. Okay, we're just finding the probability of some event that's inside of the set of parentheses. Now, in this section, there are going to be a couple of different ways of determining probabilities that we're going to talk about. So we'll look at methods for determining probabilities. The first method is the one that we use probably most often, but it's also the least useful mathematically, and that would be what's called assignment by intuition. And in assignment by intuition, we use past experience judgment or intuition to assign a probability to an event. An example of this would be when you're trying to figure out what to wear when you get up in the morning. You know, you look outside, maybe you see that it's overcast, and you think, okay, so I should probably take maybe some rain gear today. I should take a jacket and maybe wear socks and shoes and not, you know, flip-flops and shorts. Okay? So we have actually used our intuition, we've used our past experience, our judgment, our intuition to estimate the likelihood that it's going to rain today, and therefore figure out what it is that we should wear. Now, since this is assignment by intuition, there are a couple of issues with it that make it not useful in particular mathematically. Issue number one is for a given group of people, we won't all come up with the same measurement of this likelihood. If I ask people to actually quantify how likely is it that it's going to rain today based on the fact that it's overcast, I'm going to get an entire range of values. So that wouldn't be particularly useful mathematically, because mathematically it'd be nice if we could all agree on a numeric value for a probability. Also, the reason that it's not particularly useful mathematically is usually when we do assignment by intuition, we don't come up with a numeric measurement. It's not as though I look outside and say, oh, I estimate a 72% chance of rain today, therefore I'm going to wear, you know, clothing item A, B, and C. Mostly it's just, oh, I think it's more likely that it's going to rain today than not, therefore I should take some clothing that's appropriate for that. Okay? So even though this is what we use all the time to determine probabilities in our everyday life, not so useful in a mathematical context. So if that's not what we use, what then do we use mathematically if we want to calculate probabilities? The first method is called experimental, or sometimes empirical probability. And here, the results of an experiment are used to quantify probabilities. Specifically, if we want to know the probability of an event A occurring, we would run this experiment, and we would do it a number of times. And out of the total number of trials that we did of the experiment, the way to calculate the probability of an event occurring is to take the number of trials where A occurred and divide by the total number of trials. And that's how we come up with experimental or empirical probability. We actually have to do some kind of an experiment, and then on the basis of that experiment, we take the number of trials where the event that we were interested in actually occurred, divide that by the total number of trials. So for example, if I'm going to plant a garden, and let's say I have some marigold seeds, and I want to know what's the probability with this new brand of seeds that I'm using that they will actually result in a flower, in a marigold flower. For those of you that garden frequently, you'll know this, but maybe for those of you who don't garden, a lot of times when you plant seeds, some of the seeds just don't bloom. They don't ever turn into flowers. They're kind of like duds. So let's say that I plant 500 seeds, for example, and let's say that out of those 500, I don't know, 375 eventually turn into a marigold flower. So that would give me then my estimate, my probabilistic estimate of the germination rate for that new type of seed that I'm using. And again, you can either leave that as a fraction. If you did that, you would want to put it into lowest terms, which here would be 3/4. You can put it as a decimal, which is 0.75, or you can use percent representation, 75%. And all three of those are saying the exact same thing. Okay, but that's the idea with experimental probability. We actually have to do an experiment and record some results. The third method for calculating probabilities is called theoretical probabilities. And the reason it's theoretical is because we don't actually have to do an experiment in order to come up with these. So we don't do an experiment, but we use background knowledge of the scenario to compute a probability. And here, to come up with our probability, again, if we want probability of event A, and we're doing a theoretical probability, we would take the number of outcomes where A occurs and divide by the total number of possible outcomes. So for example, if I'm thinking about rolling a standard 6-sided die, and I want to know what's the probability that I'm going to roll a 2, I don't actually have to do an experiment to figure this out. I could, but I have enough background knowledge that I don't need to resort to an experiment. I know that the total number of possible outcomes on a 6-sided die, there's 6 faces and they're all different, so there's 6 possible outcomes. The number of outcomes where I get a 2, there's only one of those on a 6-sided die, so my theoretical probability would be 1 in 6, which is a fraction in lowest terms. If you wanted this as a decimal, it's about 0.17 if you round, which is about 17%. Okay, so notice in theoretical probability, we don't do any kind of experiment. We just have enough background knowledge that we can answer the question. Now, ideally, empirical probabilities and theoretical probabilities should agree. They should come up with the same numbers for the same scenario, because there should be only one probability associated, for example, with getting a 2 on a 6-sided die. But if I try to use experimental probability to answer this question, what's the probability of getting a 2 on a 6-sided die? Let's say I do a number of trials, outcome, and then probability of 2. So let's say on my first trial, I roll a 4. Well, right now, my experimental probability of rolling a 2 on a 6-sided die is 0%, because the only roll that I've made, I didn't get a 2. So far, experimental probability is not agreeing with theoretical probability. Let's say on my second trial, I do manage to roll a 2. So now out of 2 total trials, I've gotten 1 2, which gives me an experimental probability of 50% for rolling a 2. Well, that's still not anywhere close to what we know the actual probability should be, which is 17%. Let's say on my third roll, I roll a 6. So now my experimental probability is 1 in 3, or about 33% of getting a 2. Let's say on my fourth roll I get another 6. So now it's 1 in 4, or 25%. Eventually, if we kept this up and did enough trials, we would come out pretty close to this 17%. Experimental probability would eventually agree with the theoretical probability, but only in the long run. So here's something really important to know. It's called the law of large numbers. Which we can abbreviate as LLN. Okay, what does the law of large numbers say? It says, in the long run, as the sample size increases, the experimental probability approaches the theoretical probability. In the long run, as the sample size increases, the experimental probability approaches the theoretical probability. But the key here is in the long run. There is no law that covers short-run behavior. Okay? It has to be in a really long-term type of experiment. Again, you'll notice here, when we were doing just our short number of trials, even after 4 trials, we only got down to, say, 25%, and we know it should be closer to 17. We would need to do this a bunch of times. Okay? In the long run, the experimental probability would even out to about 17%. But in the short run, we can't make any similar guarantees. Okay, so this only talks about long-run behavior. A couple of other terms and definitions before we go on to the next video looking at probability rules. So sample space is another key term that you'll see in the textbook. The sample space is the set of all possible outcomes of a statistical experiment. Now when you see when you see sample space, usually sample space will be denoted by a capital S with these little serifs on the end. It makes it look kind of fancy and script-like. Okay, so it'll have these little S's. And then there'll be an equal sign. And because it's a set, when we deal with sets in mathematics, they're denoted by using these squiggly brackets, one to open the set and one to close it. And then all a set is it's a list or a collection of objects. So let's go back to our dice example. And let's say I was interested in the sample space for rolling a 6-sided die. So the sample space lists all of the possible outcomes of rolling the 6-sided die. So I would be looking at the numbers 1 through 6. And usually they would be separated by commas, and they would be closed with a squiggly bracket. Okay, similarly, I could be interested in the sample space for flipping a coin. So we would have heads and tails. Those would be our 2 possible outcomes for flipping a coin. And then let's say the other thing that I was interested in, sample space here, let's say I'm going to flip a coin 3 times, and I'm interested in the number of heads in 3 flips. So the lowest number of heads I could get in 3 flips would be 0. Then I could have 1, 2, or all 3 heads. Okay. So these are examples of sample spaces. One of the things that you'll also see come up in this section is a question of, are the outcomes in the sample space equally likely? So when we're thinking about our six-sided die, for example, excuse me, there are 6 possible outcomes, 6 faces. Each of these outcomes occurs only once in the group of 6, so they each have a probability of 1/6 of occurring. Therefore, are they all equally likely? Yes. Heads and tails on a single flip of a coin. Are these 2 outcomes equally likely? Well, you have a 50-50 chance of getting heads and a 50-50 chance of getting tails. So are they equally likely? Yes. They both have probability of 1/2 or 50%. Now here's where things get interesting. When we get down to this question of number of heads in 3 flips of a coin, are these outcomes equally likely? No, they're not. If you're wondering why, we can think about what the possible outcomes of an experiment like this might look like. I could have head, head, head. That would be one way for 3 coin flips. Head, head, tail, head, tail, head, tail, head, head, tail, tail, head, tail, head, tail, head, tail, tail. I think tail, tail, tail. Do I have them all? 1, 2, 3, 4, 5, 6, 7, 8. Yes, I do. So here's all of them. Now, how many of these 8 outcomes had 0 heads? Well, there was only one of those, right? There's only one way to get 0 heads. So that has a 1 in 8 chance. But then when I move on to how many ways can I get 1 head in 3 flips? Well, I can get 1 head here, 1 head here, 1 head here. There's a 3 in 8 chance of that occurring. It's much more likely that I'm going to get 1 head in 3 flips than it is that I'm going to get none. So these are not equally likely events. Now in the next video, we'll start taking a look at some of the formal rules that are used with probability. There are 8 of them altogether.